Hello everyone, welcome back to another video. In this video, we'll be solving the question get connected components of a graph. Now this question is really important as it has a lot of applications in future, right? Also, there are a certain prerequisites for this question, which are the question that we did has paths and print all paths. Both of those questions in which we used DFS, right? So we did those questions using recursion. That technique is known as DFS, which is depth first search. I highly recommend that you check both of those problems out. Those are the part of this continuous series. So the link to both of those would be in the description box. Please check them out first before jumping onto this question. Now, the question says that you are given a graph and you're required to find and print all the connected components of a graph. Now, what do we mean by connected components? Right? Until now, what we have seen is a graph which was somewhat like this. So we had 0 to 1 to 2 to 3, which goes to 4, goes to 5 to 6, and these were also connected, right? In this particular graph, you can travel from any point. You can travel from any point to another point. So you can travel from 0 to any other vertex that is present in the graph, right? But what happens is at times we get graphs which have other vertices like this. Now this would be entirely a single graph. But in this case, you won't be able to access 7 and 8 from any of these vertices, right? Because there is no connection between these two, right? Even if I remove this particular connection between 3 and 4, now this and this are completely isolated from each other. That means these are connected in their entirety. They are not connected to each other. These are components of a graph. These are connected components of a graph. So what we have to do in the question is we would be provided with a graph which looks like this, and we have to provide all of these connected components in the form of array list. So we would be providing it in the form of array list of array list, right? So if I have 0, 1, 2, 3, 4 over here, what I would have is this as one component, then 4, 5, 6 as my second component, and 7 and 8 as my third component, right? So this is my first, second, and third component. And these would be stored in components array list of array list, right? And this would be my answer. So this is the desired output. This is what the question wants. I hope you understood the question. I would request you to try this out on your own, as the concepts that we are going to utilize in this are already something that we have discussed in past. So feel free to experiment and do it on your own, right? So moving on to the solution of this, right? We have this graph, right? Let's draw a much simpler graph with a bit of less of vertices to work with. So 0, 1, right? Let's suppose I have 3 and 2, and then 4 and 5 and 6 over here, right? For this, we have, this is a single graph. So we have 3 components in this, right? So we have a total of 3 components in this graph. If we remember in DFS, how we used to do DFS is, we used to call from a source. Let's suppose I take my source as 0, right? From 0, I would call for all of my neighbors. I would have a visited in which I would have 0, 1, 2, 3, 4, 5, and 6, right? All of these vertices. And suppose I call for 1 from 0, right? So I would mark 0 as true. I would call for 1, and then 1 would say, what are the possible edges that I can visit? 1 would say, okay, 0 is a possible edge, but can I visit 0? I cannot, because in visited, it is marked as true. So 1 would return, right? Now 0 would say, what are the other possible edges? 0 only has the edge with 1. So 0 has also processed itself. That means while evaluating, 1 marks itself as true, right? So that means 0 would return back to what? To main function, right? So if I call with 0 as source, I would only be able to evaluate just this component, right? But what if I call for all the points, all the vertices in this entire visited, all the vertices which are not marked? As we can see, 2, 3, 4, 5, and 6 are yet to be evaluated, right? That means they haven't been evaluated as of yet. that means I can call from 2 as well. So if I call from 2, I would go to 3 and come back, and I would mark 2 and 3 as true. As I get back to 2, I would say, okay, I got through another component of mine, right? Then I would call from 4, and I would go to 5, 6, and I would come back, right? And I would mark 4, 5, and 6. So if you see, I had a total of 3 iterations. That is because I have 3 different components, right? What I did was I traversed through my visited array, and for all the evaluated vertices, I called for a DFS function, which was my recursive function that I use in hash paths and print all paths, right? So let's see how we can do this. Let's see how we can code. Okay. So if I bring this up, what we have over here is a array list of components in which we have to fill in our answers, right? What I said was we can have a Boolean visited, right? Boolean visited of size of vertices, right? So for each vertex, I would have a position in my visited array. What I did was I traversed to the visited array. I traversed through the visited array. So for int I is equal to 0, I is smaller than vertices, I plus plus. So for each and every vertex, I would check if the visited of that vertex is false or not. That means if it is unevaluated, right? If it is unevaluated, what I would do is I would call for a DFS function, right? A DFS function that we wrote, right? Which would be a recursive function. What it would do, it would traverse through the graph, through all the connected vertices, right? So at each and every iteration, I would be going through a component if possible, right? So I would have a source. What would be my source in this case? It would be I, right? So the current point, right, over here, it would be visited of I, right? So my source is I. Is there any destination in this question? No, it's not. So what we did was, if we look at over here, I just traversed from 0 till 1 and came back. I did not have anything. I did not have a base case, right? I don't have any destination. So what do I need in parameters? I only need the graph and the visited array. So I would pass the graph and the visited array. And what I would say is I would have the faith that this function would get me an array list of all the vertices that are present in that particular component, right? An array list of all the components that are present, all the vertices that are present in that component. So what I would also do is pass a array list. Let's suppose comp, and before passing, of course, I have to make that array list. So array list of integer over here, comp. So it would be just a singly array list. Okay. So we are passing this. Our faith is that the DFS recursive function that we will write will get us all the elements, all the vertices in that particular component inside the component array list, right? So at the end of it, what we would do, we would just add this component inside our components array list, right? So this is our high level code. This is what we want to achieve, right? So if we write our low level code now, which would be just similar to how we wrote our hash path function. So public static void, we don't want to return anything, right? DFS, we have a source, then we have what? Our graph. So if I take this from here, it's my graph, and if I paste this over here, then I would have what? My visited. So it's a Boolean array visited, and the next thing that I have is an array list of integer type, and it has components, right? Just a single component, right? Okay, now base case is not required because I'm just going to traverse through all of the vertices and put them inside the component. Now, very first step that we do in DFS is mark our current source as true. So my current source would be true. All right. Then I would visit all of my neighbors. So for edge E, in what? In my graph source, I would check if the current neighbor is visited or not. So I would do E dot neighbor over here, and I would check if it is false or not. And only if it is false, I would call for it, right? So I would call my DFS for my E dot neighbor, and I would pass my graph, and I would pass my visited, also my component, right? This is my basic DFS. Now, the only thing that I have to do different in this case from HashPaths is maintain this component array list, right? So while going down, what I would do is I would add my source in the component array list, right? I would add my source in the component array list. And this function would then get me all of the vertices inside a particular component, right? So our low level code is also ready, right? Now if we run this and check for any compilation errors, we get a compilation error which says that we cannot find the symbol edge in graph. Okay, there is a spelling mistake over here. This is graph. If I run this again, then this passes for the test case. If we try to submit this for all the test cases, let's see what we get. So it takes time. At times it takes time. So yeah, we are getting 10 out of 10, right? So this is a correct solution. Now, again, what we did was to look at the code again. What we did was scroll this down, right? We had a components of array list of array list, right? Okay, then we made a visited, right? We traversed through that visited. That means we took each and every vertex that we have, right? This loop gives me all the vertices one by one, right? And we checked if that particular vertex is evaluated or not. If it is evaluated or not, right? If it isn't evaluated, we evaluate this. How do we evaluate this? We call for a DFS function, and we have a faith that the DFS function would return us with all the elements of the component, right? And then we added that component in our components array list of array list, right? And at the end we printed that, right? Here we got our answer. Okay, now the DFS function has an algorithm, right? So if we observe the algorithm is simple. The very first thing that you do, the first step that you do is mark my source as true, right? And the second step that you do is call for all unvisited neighbors. This is my algorithm for DFS, exactly what we used in HashPaths and print all paths, right? So we mark our visited as true, and then we call for all the unvisited neighbors, right? And the only thing that we do other than that is add our vertex to the component, which was our faith, right? So I add myself in the components array, and I have a faith that all of my child would add themselves in the component array. That was my faith, right? So I hope you got the solution. It is a really important question, so please feel free to rewind the video if you want to and properly understand how we derived the approach, right? So the entire process of evaluating a single component and how it marks itself and the rest remain unmarked is something that we utilized in deriving the faith for high level, and then we coded for low level. And also then we looked at the DFS algorithm, right, which is a simple two-line algorithm, right? So I will see you in the next video. The next video is a simple extension of this question only, so you would be really excited if you would solve that. See you. Bye bye.